Hi, and welcome to this second clip in a series of A2 Kinetics video clips. And in the previous session, we introduced the rate equation and started to look at orders with respect to concentrations. In this clip, we're going to look at a way of determining the orders from experimental data. Specifically, we're going to use something called the initial rate. So we have seen before, and you'll remember from GCSE, that by using tangents on graphs, you can measure the gradient of a curve at a certain point in time and use that to calculate the rate at that specific moment. And if we were to then do a series of concentration variations of 3 reagents, we'll use the same 3 as we used in the previous clip, and we were to do, as I say, a series of concentrations whereby we may have A at 0.1, we'll do 4 different experiments here, 0.1, and then the final one we'll change the concentration of A, making it 0.2. We'll assume that all of these are in moles per litre to make that nice and easy. We'll say that B was 0.1 for the first 2, but then we doubled that in both of the third and fourth. And for C, what we'll say is we looked at 0.1 first and then went to 0.2 in each of the subsequent 3 experiments. That then gives us a way of comparing the variation of concentration. So if we look at the first 2 experiments here, what we've done is doubled the concentration of C whilst keeping A and B constant. And so we can see if there is any variation in the initial rate, we can be pretty sure that the variation in rate is only due to changes in C. We're just changing one thing at a time. We're essentially making a controlled experiment. If we were to measure initial rate data, what we may see is that in the first 2 second experiments, the rate changed from 4 times 10 to the minus 3 moles per litre per second. So initial rate will be measured in moles per litre per second. And we can see that going from experiment number 1 to experiment number 2, the rate has doubled. This coincides with a doubling of the concentration. And so what we can say is that if we use the rate equation as we derived in the previous clip, we know that now if the concentration has doubled and the rate has also doubled, the order of reaction with respect to C is 1. If we then look at the second to third experiment, we can see that B has doubled. Again, everything else has stayed the same. And if we see that this time it's gone from 8 times 10 to the minus 3 to 3.2 times 10 to the minus 2, we can see that this one has increased by a factor of 4. If B has doubled and the rate has gone up by 4, that has given us a 2 squared relationship, meaning that the order of reaction with respect to B is second order. And likewise, we can do the third version, whereby we look at A, and if in this example we could see that the changing of the concentration of A has had no effect on the rate, then we could evaluate that A is 0 order with respect to A. And as we saw in the previous clip, if this is the situation, we would generally not write that term, we would ignore it in the rate equation, and likewise we wouldn't need to write the 1 in the first order reaction one either. And so what we've done in here is use a method of changing the concentrations, measuring the initial rates of reactions. By isolating the effect of only one reactant at a time, we've been able to evaluate the overall rate equation for this reaction. If we were to have plotted more specific values of rate versus concentration, if we were to look at the concentration of any of these substances, A, B or C, and plot against the rate, what we may have seen is that for a 0 order reaction, we have a horizontal line because there is no variation in rate with respect to concentration. If we were to have plotted the first order one, i.e. in this situation the concentration of C, we would see a straight line going through the origin indicating directly proportional, and a first order reaction, so this would be first order, this would be zero order, and if we had plotted a second order reaction, the rate will go much more steeply and would be curved in that process, showing us that graphically we've got a second order reaction as well. But this method uses initial rate data which has been gathered from your experimentation, and as we said in the previous clip, the only way to generate a rate equation is through experimental data and not necessarily through the stoichiometric balanced equation. In the next one, we'll look at ways in which we can then use this data to calculate the rate constant for each of these equations and looking at the units of that as well. So thank you very much, and I will see you in the next one.